Alright guys, so today we started talking about a heat engine, which is a device that converts heat into work. So the whole idea with a heat engine, like we demonstrated in class today, is you have some sort of hot reservoir that transfers heat into our engine, and we call that QH. The engine does some sort of work on the surroundings, creating some mechanical energy for us. And then some residual heat is going to be transferred into a cold reservoir, which we call QC. And remember, for an engine, that if we look at a pressure volume diagram, it's always a cyclical process. Could be something like this. It will always be clockwise. And remember that we always start and end at the same position, which means delta U has to equal 0. And for the change in internal energy to equal 0, then the energy in and the energy out have to be equal. So QH has to equal work done by the engine plus QC, the heat transferred out to the cold reservoir. Another way to say that is that the work done by the engine will equal the heat transferred in from the hot reservoir minus the heat transferred out to the cold reservoir. We like our engines to be efficient, and efficiency is defined as the amount of work done by the engine divided by the amount of heat that we've transferred in from the hot reservoir. Another way to write that is the heat transferred in minus the heat transferred out divided by the heat transferred in. And yet another way to write that is 1 minus the heat transferred out divided by the heat transferred in. And so what we see is, to have a 100% efficient engine, we would have to have 0 heat transferred out to a cold reservoir. And we're going to talk about why that's not really going to be possible. Alright, so a guy named Carnot, the T is silent, started studying what would cause the maximum efficiency of an engine. And so he came up with Carnot's theorem, which has a couple basic parts. The first part of Carnot's theorem says that for a maximum efficiency engine, all the processes that the engine completes must be reversible. And to be reversible means that both the system and the surroundings can be returned to their original state. And the second part of his theorem says that the efficiency of a reversible engine, of one of these max efficiency engines, simply depends on the temperature of the hot and the cold reservoir and nothing else. So let's see how that translates into equations. So as we said earlier, the efficiency of an engine is 1 minus QC over QH. Now, Carnot made an assumption, and he said that for reversible engines, for these maximum efficiency engines, that ratio of QC over QH just depends on the temperature of the cold reservoir and the hot reservoir. So by substitution, we see that the maximum efficiency, the Carnot efficiency, the efficiency of a Carnot engine, would just be 1 minus TC over TH, which could also be written TH minus TC over TH. And either way we write it, what we see is that to be 100% efficient, even if we have this reversible engine, to be 100% efficient, the temperature of your cold reservoir ends up having to equal 0 Kelvin. And I think most of you guys know that is not exactly an easy thing to do. And we're going to talk about in a minute that that's actually an impossible thing to do. Alright, so now it's time to talk about the second law of thermodynamics. And the second law of thermodynamics deals with entropy. And you may remember from chemistry that entropy is a measure of disorder, a measure of chaos, some people call it. It's a measure of how disordered our energy is. When we have very organized energy, we have low entropy. And when we have disorganized energy, we have high entropy. And so if you think about our heat engine, we started off with a hot reservoir that was very hot and a cold reservoir that was very cold. But every time our engine goes through a cycle, our energy becomes less organized. Our hot reservoir gets a little cooler, and our cold reservoir gets a little hotter. Eventually, those two reservoirs are going to become the same temperature. This was not a reversible process. Every time we go through, those temperatures get a little closer and closer together. In other words, the entropy increases. And so basically then what we're seeing is that reversible processes do not happen. Okay? Because anytime you do any process, we are going to see that the entropy of the universe is going to increase. Things are not going to go back exactly to their original state. Which tells me the Carnot engine is not possible. But now we're going to use the third law of thermodynamics and talk about what would happen even if it was possible. So there's a couple ways to interpret these laws of thermodynamics, but one of the ways to interpret the third law of thermodynamics is that it is not possible for an object to maintain a temperature of 0 Kelvin. Basically, we know if an object is colder than its surroundings, then heat's going to transfer from the surroundings into the object. And there's no way to have absolutely no heat transfer in, so there's no way we're going to maintain a temperature of 0 Kelvin. So if we go back to our maximum efficiency for a Carnot engine, 1 minus Tc over Th, this cannot be 0. Okay, and so Emax will always be less than 100%, even for one of these ideal Carnot engines. So, just to review the difference in a heat engine and a heat pump. Remember, an engine, we put heat in and we get work out. And if we're ever looking at a pressure volume diagram for a heat engine, it doesn't have to be a triangle, but it's always going to be a clockwise shape, so that the area under the curve as the gas expands will be bigger than the area under the curve as the gas is compressed. Heat pump will always be the opposite. Even if we had the same points on our graph for our heat pump, which we may not, we would see that our cycle would go in a counterclockwise direction. Because for a heat pump, we are putting mechanical work in and we are getting heat out. And so now we see that the work done on the gas as the gas is compressed is going to be bigger than the work done by the gas as the gas expands back out. So for a heat engine, the work on for the cycle will always be negative. The work by for the cycle will always be positive, and the Q for the cycle will always be positive. So we're putting heat in, we're getting work done by the gas. But for a heat pump, the work done on for the cycle will always be positive. The work done by for the cycle will always be negative, and Q for the cycle will always be negative as well. And so in this case, we are putting work into the system by doing work on the gas, and we are transferring heat out of the gas into the surroundings. So that's the big difference in a heat engine and a heat pump. And that's it for today.